So our next speaker is Mahimna Kelkar from Cornell as well, and the title is entitled "Fair Ordering in Byzantine Consensus." Mahimna Kelkar is a PhD student in computer science, advised by Ari Jules at Cornell. So take it away, Mahimna.
All right, let me start talking about some of the protocols that we have on fair ordering consensus. So I'll start by briefly recalling the state machine replication or consensus abstraction that is sort of the core mechanism behind blockchains. So traditionally in like the classical or permission setting, there's a set of servers that receive transactions from clients, and the goal is to order these transactions in a consistent manner. And some of these servers could be faulty or actively malicious, but even then security should still hold. And in the permissionless setting, let's say using like proof of work or proof of stake, these servers are replaced by miners, but the abstraction is basically the same, although miners can enter or exit the system at will. So usually we expect two properties from consensus protocols. The first is consistency, or sometimes called safety, and the second is liveness. So consistency ensures that honest parties will eventually agree to the same view of the final log, and liveness means that new transactions that are sent by these users will be incorporated into this log soon. But unfortunately, neither consistency nor liveness provides any guarantees on the actual ordering of transactions. And quite often, it's very easy to manipulate this order. For example, when looking at classical protocols, where a leader proposes an extension to the ordered log and the other replicas can follow along, like PBFT or Paxos. So in some protocols, the leader gets voted out only when it's acting maliciously. Some protocols like Hot Stuff rotate the leader every once in a while. But in all of these protocols, like whoever the current leader is, it can propose any transaction ordering. So it has the power to arbitrarily manipulate the transaction ordering. And no prior permission protocol kind of guarantees any fairness in this. And permissionless protocols aren't really much better either. Even if they're fundamentally more decentralized, they still have complete control over the ordering and inclusion of transactions given to the miner. So this is what we call like an ephemeral or short-term centralization specifically for ordering. So why is something like fair ordering very important? So the primary motivation is seen in the context of decentralized finance, or DeFi, which is pretty hype right now. And this is just like a partial list of financial instruments on the like the Ethereum ecosystem that have popped up in just the last few years. So let's take like a simple example to see how ordering affects transactions. So let's take the case of a decentralized exchange where you have a user Alice trying to trade Ethereum for Uniswap tokens. So decentralized exchange is something that allows a user to swap between cryptocurrencies at a rate that's programmatically derived from the exchange. So let's say the user Alice can swap in one Ethereum token for 100 Uniswap tokens at this time for one particular ordering. But for a different transaction ordering, Alice could get like a worse price of, let's say, just 98 Uniswap tokens. So basically it means that an adversary that can manipulate the transaction ordering can profit from the difference of these exchange prices by carefully manipulating the transaction ordering or inserting its own transactions. So something that can be done is like front running, where you insert your own transaction before Alice's. And effectively, the end result is like the attacker is stealing the profit that Alice could have made from the trade. And this is quite reminiscent of front running and high frequency trading on Wall Street, as popularized by the Michael Lewis book Flash Boys. And in fact, this is the same kind of front running that was quite rampant on permissionless blockchains like Ethereum, as shown by Phil's work on Flash Boys 2.0, as well as a number of more recent works. And what's interesting is all of this can be done even through bots that are not even in charge of the ordering, and much more catastrophic problems are caused by miners who are in charge of the ordering. And Phil's work found that MEV, or this problem of adversarial ordering, affected real world users with adversaries extracting money from them, basically ordinary users. So essentially, Phil talked about this in his talk as well, where when I talk about adversarial manipulation, I'm really talking about different kinds of tactics that an adversary can do with the transaction ordering so as to take money from the system. So for example, a miner can censor specific client transactions or insert its own transactions before or after a client's transaction. They can reorder specific transactions. could be like bribed or collude with a client, and all of this can be done like blindly without actually knowing the transaction data as well. So this term MEV is sort of the quantification of the value that's extractable from the system by any kind of manipulation of transaction ordering. And in the last few years, the study done by Flashbots, just for a few contracts on a few DeFi contracts on Ethereum, has seen over like $750 million extracted in just like the past like year and a half. And MEV may kind of pose bigger threats in the near future, and recently in light of the proposed EIP-1559, which cuts transaction fees that are sent to the miner. Mining pools have already begun to add front-running software to make up for the lost profits. Like we have Ethermine that's already started to add like front-running software to recoup the losses from the lost revenue of transaction fees. What's more problematic is some miners have been begun to like auction off the right to choose the ordering in the block to the highest bidder. So this is what we call MEV Auctions, and this is something that Flashbots has been doing quite recently. The goal of MEV Auctions was essentially to make MEV more transparent, but in the long run, it actually makes the problem of ordering significantly worse. And what's more is all of these MEV auctions are currently centralized, like Flashbots or Background.me by Blockstrat, which you need to kind of trust the operator of the system, and making like the whole system more centralized rather than decentralized. And another problem is that the rich get richer because only those searchers who are able to spend a lot of money to find the best ordering can bribe these miners and extract the value from the system. So basically the claim is miner extractable value auctions can make centralization worse, not better, as it's argued by their proponents. So we sort of need a more fundamental solution to this problem, which is some of the work that I've recently focused on. So our work focuses on solving this manipulation problem at the consensus layer and makes it completely agnostic to the underlying application being considered. So some DeFi applications like decentralized exchanges will definitely benefit from this, but it also abstracts out the incentives for manipulation so that it can be used even in like non-DeFi contexts that benefit from ordering guarantees, like ICOs or first come, first serve kind of sales. So we aim to sort of handle a more broad notion of order manipulation that's not just restricted to front running or censorship. And in general, the goal is to consider any way that an adversary could mess with the ordering. So for instance, our notions will be stronger than something like threshold encryption or committed reveal that can that are not really resistant to metadata or collusion with the miners. It's also stronger, notably, than choosing a random ordering where you can just try to flood the network now and have your transaction maliciously be ordered first. But what's pretty cool about this is our techniques can still be combined with these other threshold encryption and committed reveal schemes for more stronger guarantees. So let me talk a little bit about how we define fair ordering. So this is part of a paper that we published in Crypto 2020, joint work with Fan Zhang, Stephen Goldfair, and Ari Jules, where we define this notion of receive order fairness as basically saying if a majority of nodes are input some message M1 before M2, then all of the honest nodes will deliver M1 before M2. And this is kind of a nice notion, but unfortunately it's not always achievable in practice. To understand this kind of paradoxical instance, let's take an example of how global ordering can be non-transitive even when these like individual orderings are transitive. So here we can see, let's say we have 3 miners that receive transactions in this order, and you can see 2 nodes have received X before Y, 2 nodes have received Y before Z, and 2 nodes have received Z before X, which if you look closely is basically a cyclic ordering, which means that in some cases, receive order fairness can't really be satisfied. So we prove in our paper that it can be satisfied under some strong synchrony assumptions, but in the general case, it's not possible to satisfy. So the next thing we kind of want to do is how do we weaken the fairness requirement? So basically the goal is that choosing a good fairness definition is kind of critical to the protocol in that it should be achievable, so it doesn't have some kind of paradoxical impossibility result, and it should not be vacuous. So it should really be able to prevent the front-running attacks and the order manipulation attacks that happen in practice. Some natural definitions that we actually tried out that don't work are some kind of median timestamping based approach, or using a separational time barrier and considering transactions that are before the time barrier and after the time barrier as distinct. What we did settle on is what we call batch order fairness, which is a kind of minimal relaxation from receive order fairness. Basically, the only relaxation is when a majority of nodes receive M1 before M2, then honest nodes should deliver M1 no later than M2. And this kind of allows us to deliver these non-transitive paradoxical orderings into the same batch. And we show that in some sense that block or batch order fairness is a minimal relaxation of receive order fairness, especially when we talk about the Condorcet paradox. And it kind of reduces to receive order fairness when there is no paradoxical orderings. And fortunately, it is achievable in practice, and it's not made vacuous for standard like order manipulation attacks. So I'll proceed into talking a little bit about our fair ordering protocols. The first one that we had was Aequitas, which is a permission fair ordering protocol. So Aequitas takes place in 3 stages that we call the gossip stage, the agreement stage, and the finalization stage. And each transaction sort of goes through these 3 stages before being output to the system. So then the first stage, the gossip stage, all of the honest nodes broadcast transactions that they've received to other nodes. And at the same time, honest nodes store the broadcasts received from other nodes in their kind of local logs. And we guarantee that honest nodes have consistent local logs compared to other honest nodes. The second stage is the agreement stage, in which we agree on which local logs to use to order a specific transaction. And this actually can be done by a simple variant of the standard Byzantine agreement, and will guarantee that nodes use the same local logs to finalize a transaction. The last stage is the finalization stage, which actually outputs the final ordering of the transactions. And this step is leaderless and requires no extra communication. And essentially, this can be done because at the end of the agreement stage, all of the nodes have agreed on which data to use to order a transaction. So basically, in the finalization stage, to order 2 transactions, we look at if many of these local logs contain a transaction tx prime before tx, and then we say that tx is set to wait for tx prime. And these relations we view in the form of a dependency or weighting graph, where vertices represent transactions and edges represent transactions waiting for each other. There's 2 problems that still need to be solved in this kind of leaderless finalization. The first is that the graph may not yet be complete or connected when there's sort of no clear winner for transaction pairs. And the second problem is that the graph may not be acyclic because of the Condorcet paradox that I mentioned earlier. To solve the first problem, we basically wait for a common descendant to show for the transactions that are currently without an edge to the graph, and then order using the maximum number of dependents. And basically, we can show that this still provides a consistent ordering, because once the common descendant shows, the difference in the number of dependents stays constant. The second problem of cycles, to solve that, we basically compute the condensation graph by collapsing the strongly connected components of the initial graph, and then deliver transactions in the same component into the same batch. So basically, when there's no cycles, there's no Condorcet paradox active. This essentially means that we get 1 transaction per batch, and we end up satisfying the stronger receive order fairness definition. So our synchronous protocols take n greater than 2f over 2 gamma minus 1, where gamma is the order fairness parameter, and f is the number of adversarial nodes, and asynchronous protocols require n greater than 4f over 2 gamma minus 1. A very cool kind of outcome of our result is that we can basically build a general order fairness compiler. We only require really weak broadcast and agreement primitives that can be realized from any consensus protocol. So we can take a general consensus protocol and basically have our compiler transform it into a protocol that also provides fairness. I'll talk briefly about how we move to the permissionless setting, which is some recent work we did with Sobig Deb and Srinam Tandon from the University of Washington. So our main strategy at a high level to convert to the permissionless setting is kind of convert to an analogous problem in the permission setting. And then we'll use the Aequitas finalization technique from the permission protocol to determine the fair ordering. And for this, we highlight what's called a player replaceability lemma, which I'll really only describe abstractly here. And basically, we allow the continuation of transaction orderings from other nodes. And now we can use proof of work mining to build this continuation of transaction nodes. And essentially, we now use the finalization stage from the permission protocol to get the final fair ordering. So we provide two protocols in our paper. The first one is kind of a simple single chain protocol that relies on like proof of work longest chain. So let's say we basically split the single chain into k semantic chains or k orderings that will determine like k orderings in like a virtual permission setting. So in this diagram, we have, let's say, 3 modular chains. One is the blue modular chain, one is the green one, and one is the red one. And all blocks in the blue chain are kind of logical continuations rather than proof of work continuations. And so all blocks in blue chain are kind of one ordering, all blocks in the green chain are one ordering, and all blocks in the red chain are one ordering. And nodes that are mining these proof of work blocks try to continue the transaction ordering from the previous logical connection block rather than the previous like proof of work hash block. So every transaction is essentially mined into each one of these modular chains once. So every transaction is mined like k times, and each of these modular chains represents sort of an ordering of transactions. So these k modular chains, as I said, can be thought of as like k virtual parties in a permission protocol. And we can now use our Aequitas finalization technique, which is the third step of our permission protocol, to compute a fair ordering. I'll also note that we have a sort of more parallel protocol design where we can mine these k semantic chains or k modular chains simultaneously using a proof of work P for 1 kind of mining technique from previous literature. This is quite intuitive, but the proofs are somewhat complicated, so I won't go into them in detail. But again, we can use the Aequitas finalization technique to get a fair ordering from these parallel chains. All right, I'll talk a little bit about the some of the cool applications that come from fair ordering protocols. So one sort of powerful consequence of fair ordering protocols is the ability for honest transactions to be soft confirmed or locally confirmed in synchronous networks, even in permissionless settings. So notably, this can be done without any block being mined, and we can provably show that if you have a fair ordering protocol, then you can't have this transaction displaced by a conflicting transaction, which is something that can actually happen in current systems like Bitcoin or Ethereum. So basically, all our fair ordering protocols satisfy soft ordering in permissionless settings, and you can soft confirm within 2 delta time. This is sort of comparable to the latency and permission protocols, like sync hot stuff, for example. And even though an honest transaction is not yet mined and it's not globally confirmed, a node can locally confirm this transaction with the guarantee that it won't be invalidated. So basically, this is something powerful because we're predicting something about the future of the global transaction ordering without really knowing what's going to happen. So this is kind of useful in the payment example of, let's say you want to buy something from a coffee shop, and now instead of waiting for confirmations to go on the blockchain, you just need to wait for basically one round trip around the network in a synchronous network, and the coffee shop owner can be convinced that there won't be a double spend of this coin. A few more cool applications of fair ordering, or let's say in like decentralized exchanges, to prevent front running and arbitrage and give users fair transaction prices as opposed to some kind of random ordering. We can also use fair ordering protocols in fair ICOs where you want to incentivize first come, first serve, or let's say like give a better price for the first 1,000 people who want to buy tokens. You can also use it in like fair auctions to prevent temporary censoring of bids received before closing time. So our work is sort of the first to formalize a fair ordering property that's useful for decentralized finance. And order fairness is really important for a lot of blockchain applications, and we're really starting to just scratch the surface right now. I'll like to give you a little bit of a sneak peek into new work. This is joint work with Sobek, Sishan, Ari, and Shriram. So some of the problems that we had with the original Aequitas protocol were this thing we called weak liveness, where Condorcet cycles can chain for arbitrarily long in the worst case. It does depend on the input ordering and not on the adversary, but basically determining when the current cycle ends can take arbitrarily long. So it's hard to convert this to a leader-based protocol that's efficient, since cycle may extend across multiple leaders and initial leaders will not be able to output anything. The other problem was the communication complexity, even in the best case, was cubic, which could be even worse if we're using the generic compiler. So we do have a new protocol that will be out released shortly, which is leader-based and works in partially synchronous settings, so kind of similar to standard protocols. Although it is leader-based, we do provide the ability to prove and verify fairness, so we're not really losing out on any fairness. So we have ways for the replicas to verify the fairness of the ordering proposed by the leader. And basically, we also allow this to be bootstrapped from any leader-based protocol with no asymptotic overhead and pretty comparable practical efficiency. And we run our experiments using hot stuff. So the core idea, I'll just let you in, is in practice, the transactions in a Condorcet cycle will still need to be totally ordered. So something that Aequitas proposes to do it like deterministically, like alphabetically. But one key observation we make is in practice, it might not be terrible to output these cycles contiguously rather than together. And this leads to a powerful kind of observation, which is that the next leader can continue the same cycle from the previous leader without really losing any liveness. And this is what we do in our protocol, and provides like comparable efficiency to standard permission protocols. I'll end with some very briefly about open questions, and some of these slides were added because of Phil's punches in the previous talk, so bear with me. So basically, one thing we'd like to understand is quantify the efficiency and fairness trade-offs in practice. So understand how useful a given fairness definition is practiced by trying to attack the fairness definition based on different adversarial thresholds and rationality assumptions. Another sort of interesting future research direction is how do we analyze the composition of fair ordering protocols. So let's say we have two different L2 fair ordering protocols. How do we understand the unfairness that's caused due to the composition of these two protocols? What happens when the L1 chain is like standard, like Ethereum, and you have a fair ordering L2 chain? Does that actually lead to worse fairness than if L1 was just made fair? So these are some like open questions that we do want to answer next. One thing I'll talk about, because Phil talked about interoperability in his talk, and that there's no sort of one true definition of fairness. But here's sort of the conjecture I'll make is MEV from the composition of two good or fair protocols will be smaller than the MEV from the composition otherwise. And intuitively, I can back this up by saying like the distance between two fair ordering protocols will be small, as both of these will be kind of close to some global notion of like send ordering, or like an ideal world notion. So essentially what I'm claiming is both intra-chain and inter-chain MEV can be minimized if all the corresponding components have some fair ordering protocol. They may be different fair ordering protocols, but they have some kind of fairness associated with them. The other kind of big open question is how do we incentivize honest behavior, in that like current fairness protocols require some kind of honest majority or supermajority. So how do we deal with, let's say, like rational players or all nodes being rational? So I will say that this is currently like an open problem, but it is also somewhat of an unrealistic expectation. So for example, like proof of work or proof of stake is not completely resistant to rationality under collusion. So if you have a 51% collusion of miners in the network, they can short the system, but this is not something we see actually happen. So basically,
4-minute warning.
We want to design fair ordering protocols that also have similar guarantees of destroying the system as in like current designs. And actually, all hope is kind of not lost because fair ordering is somewhat already resistant to non-colluding rationality. So to give you a very specific example, if you have all the miners being rational and they're sort of trying to front run the user's transaction on their own, so without any collusion, they will try to insert their own profit maximizing transaction before the user. And what's going to end up happening is the user's transaction will always be output first because these irrational miners are sort of competing with each other instead of colluding. And this is something that we see with selfish mining as well. When more people try to act rational, it decreases the amount of money that you can actually make from selfish mining. So this might just be a problem that just solves itself and we don't actually need to worry about it. Another thing I'd like to kind of point out is Phil said that MEV is fundamental, so all is lost. And I personally think that this is a very pessimistic statement. Yes, the goal is to make MEV as small as possible. It is an open question to see if MEV can be made zero, but likely it can be made small enough that extracting is not worth it. And this is kind of a world that would be great to live in because even if there exists some MEV in the world, which might always exist due to composition, if it's not worth the money required to extract it, then it doesn't make sense for it to extract it and it will be left on the table as opposed to what Phil was saying. And that sort of concludes my presentation. Here's like my email address if you want to reach out, as well as a link to the webpage. Always happy to have more discussions on fairness and fair ordering protocols in general.